Hello, here's another moments question. This one, I think it's an Edexcel question from 2018, and I've had this one waved at me quite a lot over the years because it seems to scare people off with the amount of words in the question, how few numbers there are. But it's pretty straightforward really. Once you get into it, you just like with all these questions, just take it step by step. Don't get intimidated by what you're looking at. Um, and yeah, let's just go through it a little bit at a time. So they've given us a picture. We do the usual thing and find what's in the text that isn't in the picture. We've got a plank AB, mass M. I haven't put that on, so let's start adding our forces to the diagram. So we've got an MG, capital MG there. Rest with its end at A on a rough vertical wall. So we're going to have friction going up the wall, trying to keep that end of the wall up. So I'll call end of the plank up. So I'll call that F. The plank is held in a horizontal position by a rope. One end of the rope is attached to the plank at B and the other end is fixed to the wall at C. Right, so let's put in, well, I've got to add the normal reaction force because we've got a contact point between the plank and the wall. So perpendicular to the wall, we're going to have R, we're going to have tension in the rope. I'm just going to draw it at that end because we're likely to be concerned about the plank rather than what's going on at the wall. So I'm just putting all the forces for the plank on. What else have we got? The small block of mass 3m is placed on the plank at point P where AP is X. Right, I haven't put on the weight of that. So that's 3 mg. So it's quite a heavy block, 3 times the weight of the plank. The plank is in equilibrium in a vertical plane, which is perpendicular to the wall. So they always have to put those bits in. That's just showing that the plank isn't going off at an angle, some angle from the wall. Okay, it's horizontal, but it's not tilted off in one side or the other. It's coming straight out from the wall. So yeah, so that's all good. The angle between the rope and the plank is alpha. They've marked that, and tan alpha is 3/4. Now, I do like a tan alpha is 3/4 because that means we're going to have a Pythagorean triangle kicking around. That's our angle. That's going to be a 3, 4, 5 triangle. So if we know that tan alpha is 3/4, we've got that sine alpha is 3/5 and cos alpha is 4/5. Plank is modelled as a uniform rod, block model as a particle, rope model as a light inextensible string. Wonderful. Using the model, show that the tension in the rope is this. Right, so we've got this plank in equilibrium. Now we've had equilibrium questions before just for point particles, and there we just resolve in 2 perpendicular directions and solve simultaneous equations. The only difference with having moments is we've now got something else we can add in. We can still resolve in both directions. And now we can add in moments as well because we need to have rotational equilibrium as well as our translational equilibrium. So yeah, we're just adding one more equation to the mix really. So let's have a look at what we're going to do with this. The most unknowns we've got are kicking around here at point A because we've got F and R there. We want to know what T is, and we can see that they're happy for us to give the tension as a function of M, G, X, and A. So if we take moments about A, then all of those other things will be left in and everything should be fine. So let's go for moments about A. So if we're in equilibrium, rotational equilibrium, our clockwise moments will be equal to our anti-clockwise moments. So we've got mg, this is going clockwise, so we've got mg times a because it's halfway along the plank, plus 3mg times x. So that's the weight of the plank and the block going clockwise, and then we've got the component of the tension which is going anti-clockwise. So that's got to be equal to T sine alpha. And we've already said that sine alpha is, what did we say it was, 3/5. Oh, and 2a. I missed out the distance. We've got the force, of course, we've got the 2a as well. So that's 2a t, 3/5 times 3/5. So all we've got to do is solve this now for t. So that's great. Let's factorize the left-hand side. We've got an mg there, a plus 3x. So that's already looking good because that's a large chunk of what we've got in what we're trying to show. We need to multiply by 5 from the right-hand side. We need to divide by 6, and we need to divide by a. And that is going to give us t, which is 5mg over 6a multiplied by all of that. So that's fine. So yeah, I mean, with moments, you can take moments anywhere about any particular point. It'll still be correct, but you really want to be picking the point where you've got the most unknowns, or at least the unknowns that aren't in the answer that they're trying to get us to show here. It's nothing to do with reaction forces or friction or anything in that. So yeah, let's use A. Right, the magnitude of the horizontal component of the force exerted on the plank at A by the wall is 2 mg. So it's telling us that R is 2 mg. That's what it's told us here. R is 2 mg. So find X in terms of A. Right, well, this should be fine. We've got, well, we haven't done any resolving yet. So let's resolve horizontally, because they've just told us something about R, and R is in the horizontal direction. So we've got that R, which is 2 mg, must be equal to T cos alpha. T cos alpha, oops, missed out the S, T cos alpha. We know that cos alpha is 4/5. So we've got 4/5 times all of this stuff on T. So that's going to, 4/5 times 5/6 is 4/6, which is 2/3. So we've got 2/3 mg over a plus 3x. What were we trying to show? Oh yeah, x in terms of a. Well, that's fine, because now we can cancel the mg's on there, and we've just got a single equation with a's and x's. We can also get rid of that 2 with that 2, multiply through by the 3a. So we've got 3a is equal to a plus 3x. So x must be equal to 2/3 of a. Excellent. Yeah, so we put all of that together. We've got x is 2/3 of a. So yeah, they've drawn it in a, as they often do in these pictures. That was just the thing that made me pause. They've drawn a, for x, so put P on the other side of the centre of the plank, but really it's not there in this particular case. P could be anywhere, so don't just go by what they've put in the picture. Don't let that put you off. 2/3 of a is over here. That's where it is at the moment for this particular case of having the reaction force at the wall being 2 mg. Right, the force exerted on the plank at A by the wall acts in a direction which makes an angle beta to the horizontal. Right, so the forces acting here at A are F and R. So we've got R going that way, F going that way. So we've got this angle here, beta. So tan beta is going to be F divided by R, opposite over adjacent. So this is all we have to work out here, F divided by R. We might as well resolve vertically. That's going to get F in play. So if we resolve vertically, we've got F plus T sine alpha. Let's just go straight for the 3/5 of T. Has got to be equal to 4 mg. So that's resolving that way. We now know that x is 2/3 of a. So t has now changed. Let's rewrite t off of the back of this. So we've now got a 3a inside this bracket. So that a is going to cancel on the outside and the 3. So we're going to have 5/2 mg in this case. We've now got 3/5 of that. So that's going to give us 1.5 mg's. F is now equal to 4 mg minus 1.5 mg. So that's 2.5 lots of mg. 5 mg over 2. So that means that F divided by R is 5 mg over 2 divided by 2 mg. So that's 5 over 4. And that is equal to tan of beta. So that was all good. The rope will break if the tension in it exceeds 5 mg. Explain how this will restrict the possible positions of P. You must justify your answer. Okay, so everything we've done so far, or at least for parts B and C, have been fixing P. We've placed it at this point of 2/3 of A. If we move P further and further to the right, then that's going to increase the tension in the string, because we can see that the tension is, well, it's a function of x. T increases as x increases. So if we want to make the string snap, we need to increase x, and we don't want T to exceed 5 mg. So that means that we're going to have A plus 3x divided by 6a to be less than or equal to 1. Because I've just cancelled the 5 mgs on these. So that means that we've got 5a, so x must be less than equal to 5 over 3a. As soon as you go past that point, it's just too much for the string and it snaps. So you'll see with this, I mean, it's not massively different really from what we've done before. Okay, I haven't had many things with numbers in here. The only thing we've really had is this 3/4 for tan alpha, so get used to using that. They like dropping this in quite a lot. Don't immediately start jumping around to your calculator for working all of these things. I mean, not that it's going to slow you down much. It will show you immediately what the value is, but a lot of these numbers are going to be cancelling. Otherwise, we've resolved horizontally, we resolved vertically, which is stuff we're very familiar with, and then we've taken one lot of moments. Now, you could have done more moments on all of this. You don't have to keep resolving. I mean, I find resolving usually ends up being a bit quicker and easier, and we do it more, maybe more familiar with it. In these later parts, we could have taken more moments. You know, we could have taken moments about B, and then that starts bringing F and R into everything, takes T out of it, gets a relationship between F and R, and then we can divide F by R in order to get the tan beta. But there isn't really any need to do it when the resolving is so simple. You know, we've only got 5 forces acting on the plank, and 3 of them are already in these perpendicular directions of horizontal and vertical. It's only T, and we've got such an easy function for the angle that we might as well just go with resolving. But for something that looks really intimidating, and in some ways it is compared to pure maths questions, well, they'll just say something like, oh yeah, integrate this. It's not even a sentence that they're asking you to do, and you just sort of, you know, plod through the motions. This has got a lot of text in it, but you know, a lot of it isn't really that important. They're saying a lot of things. You just need to get used to going through. I mean, how much did we actually pick out in the text here? We picked out that M, that 3M, and that 3/4. All the rest of it is just saying what's already there, or just going through the usual boilerplate stuff that they have to say about uniform rods and all of this. So yeah, I like this question. It hits a lot of the points we want to be covering.